So Rosa, please.
Christoph had an emergency and...
Yes, I just have to send us. Christoph is really sorry, he got a small delay, so he proposed to give the talk on Mistral tomorrow.
Yes, so Rosa will now speak on DOTI observations of gravitational wave sources during O3. Rosa, please.
Okay, good morning and good afternoon if you are in France. My name is Rosa. As you know, I'm a postdoc of Fabio De Colle at UNAM, but in another institute, Instituto de Ciencias Nucleares, and I'm going to speak what we do with DOTI at the observatory. Just to know, DOTI is almost next to what is going to be Colibri. It's around 100 meters far from Colibri. And what we do, let me just give a really brief introduction. But we know that the gravitational wave detection 4 years ago, the 700878, it had been the only simultaneous detection between some gravitational wave and the electromagnetic part, and it was a real spectacle because everybody in the science and in the collaboration observed this event in the summer, unfortunately for us. But just to know what happened when LIGO sent us the alert with another instrument like Fermi and Integral, which are gamma ray burst detector, reported also a signal that come from there, and after that the optical and infrared bands also detected an electromagnetic counterpart. This is the signal of the gamma ray burst associated, and this is the signal of the kilonova. And what is a kilonova? I did a video just to explain. We have no, again. Just let it because no. We have a binary system of neutron star, or at least one neutron star in a system of binary compact objects. And what will happen there? If they collide, it launches a relativistic jet. This is known like the short gamma ray burst, and it's short only because of the progenitors, and we have another kind of gamma ray burst. But if we have a lot of neutrons, because it was the consequence of neutron star collision, we have a lot of neutrons here around of the system, and we have also the tidal ejecta and an accretion disk, like always, and neutrinos. But the important thing here is that all the material here is very rich in neutrons. And what it happened next, that if we have a lot of neutrons, we produce, or it produces the air processing. That this is not more than if you add more neutrons to an atom, and it creates a heavier atom. And this is how is created metals in the universe. And that's all for my video. And you know now what is a kilonova. Yes, that's all. Okay. And what's the importance of a kilonova? Well, if we know how the kilonova is behaving, we can know how is the arrangement in the universe, and we know how the progenitor could be. The question of the states, if are involved winds, magnetic fields, the fraction of electrons, the spin, in the case that we have not just a binary neutron star system, but also with a black hole. And as I said before, an accretion disk, neutrinos always, and how it's going to be the remnant if we have a supermassive black hole, a magnetar, hypermassive neutron star. And just to know, because we only have one detection, And I just want to highlight this because theoretically we have a lot of models. This for each line is a different theoretical model of a kilonova, and you know it covers a lot of range of magnitude. Then everything related with these parameters will be plugged in this graphic, and what we want to do with the detection of more kilonova is to constrain what is this, or what of these models can be correct or not. Well, LIGO. As you know, LIGO is a collaboration dedicated on the detection of gravitational waves, and it had been 3 runs at this moment, and everything, every time that LIGO begins another run, has a better sensitivity. And what is that? Well, it comes to more alerts, more candidates of gravitational waves. And for example, you could see that in 1 year, the last run that we studied with DOTI, it was 56 alerts instead of the 3 alerts in the first run. What's the problem here? The LIGO for the configuration, and you know, are interferometers, and the area where we are going to search for the electromagnetic counterpart is not enclosed region, but also is a huge area in the space. We typically could think that it's going to be an easier task. Why? Because we had one detection then. But this detection was a very special one. Why? Because it was a very well localized, but also very close to us, only 40 megaparsec. And on the other hand, we have not the lucky to repeat that. And in the last round, we have error boxes about 1,000 square degrees to search the signal of a short gamma ray burst or a kilonova. Then it complicates a lot of things. But to map all these huge regions, DOTI was designed 4 or 5 years ago, and it consists in 6 telescopes of 20x diameter each one, mounted in the same platform, in the same thing. And we have it works with a clear filter. It reaches about 80.5 to 20 magnitudes in about 1,000 seconds of exposure. But the interesting thing here is that DOTI can map almost 70 square degrees per exposure. Then the problem here to map these huge regions that would be impossible with a typical telescope with a small field of view is, and it represents a challenge, is faced with the very satisfactory. And in the last run, we observed more than the half of the events, and in the we have a paper published, and we explain what we observe, and if not, why. For example, just to know, sometimes the error boxes were too large, and it was impossible to follow up with search zones. But sometimes we had them. The observatory was closed, was too solve for us. the weather, maybe it was rain or clouds. It was maybe too close to the sun, the preliminary location, or we have two alerts in the same night. And we have to decide what observe or not. And another interesting thing, if you remember the light curves of the kilonova models, is that the peak appears around 12 hours one day after the trip. Then we have to cover the region of the sky very quickly in order to maximize our possibilities to detect something. Then we also put or stand out in our results that we were very fast to cover the region and to begin to map the probability map that LIGO sent us. And for example, just in the case, for example, this event, it was this is related with a black hole, and is in the mass gap between another black hole and or a neutron star. And this is the kind of map that the probability map that LIGO sent us. Here is the probability in purple, and these are the regions that DDOTI cover. The H square represents the field covered by a single telescope. And in this case, we have an excellent localization. It was very easy to cover all the region. And this is here is show how this is the sun, obviously, and this is the region that DDOTI could map each in this night. Here is the position of the moon, and this is at the beginning of the night and in the end of the night, and this is the combination of two of these two times. But for example, I just let me put this here. Sometimes we have the problem of the part of the region where too south for us. Then we only cover what is in our limit, of course. And you know, you can see here that the regions are not always the same. Here we have the fortune that it was an enclosed region and not appears to be spread for all the sky. But it's not the same to observe this, that is very, very small region, than this. And we need more fields and of course more time. What we did, because nobody detects nothing, we tried to, well, we studied what could be our probabilities to detect short gamma ray bursts, taking into account the sample of events that have been detected in the last, no, all the short gamma ray bursts that have been detected ever with a redshift well determined. Why? Because we have to put our probabilities against the distance. And we did this with taking into account if we have a deeper limit around 20.5 or unfavorable condition, that it would be a very, very shallow limit. And of course, if we don't have a good performance, we have less probability to detect something. But if we have good weather conditions, we can achieve deeper magnitudes, and also we maximize our probabilities. Then, just to remember, the event that was detected 4 years ago, it was around here, 40 megaparsecs. Then, of course, it was detected for everybody. But if you go far, probabilities are smaller, of course. And on the other hand, we put all the models of the kilonova that I showed you before in a plot, just to know what could be our probabilities or the chances to detect something related with a kilonova. And how we did that? Well, if you remember all the light curves that I showed you, they were related with different kind of models. Related with where it was the central engine and some specific models that are very interesting for theoretical people. And we put here our limits. These are the different upper limits that we obtain in the O3 run with DDOTI. And these are the different models just shifted different distance. And what we can see, of course, is that we could have detect an event like this was the kilonova detected 4 years ago, 70 years old. It could be detected, this is the slide, and for our limits, typically we could have detected at most at 200 megaparsecs. And for example, we know that for the brighter models, we have upper limit here. The brighter models are these cyan region, and we have our upper limit here. And this means that if there is something here, we would have detected. We don't have anything, then there is nothing here. And we can project these brightest models related with magnetar power kilonova. And we did that. And this is why it's important to do these studies, because even with no detection, we can do science with our data. And what about for the future? Just let me close my window because I live next to the school. For O4, that this is the next, is going to begin in 3 months. The LIGO and Virgo collaboration have more sensibility, but also more interferometer. No, this is for O5. And this converts in more distance to detect signals. And then, of course, the prevision, the prediction are very promising. But specifically, we are going to have for the next round 5 times more of candidates to gravitational waves, and of course we maximize our probabilities to detect something. We in the last round we have around 1 alert per week, but in the next round we are going to have 3 to 6 alerts per week, almost 1 per day. But the important thing, because this is really general, but the important thing with DDOTI is that the LIGO promises us really small regions to our box, and this turn on this region, 33, 50, and 41 square degrees to cover per alert. And if you remember that you can observe 60 69 square degrees per image. Then we can cover all the region in one exposure. And how is important this? Because we don't have to spend too much time just to changing our visit. We can stay in the same region of the sky and achieve more deeper exposure. And this is how we can also improve our probabilities to observe an electromagnetic counterpart, even if it's faint. And the conclusion, what I told you, we observe more than the whole. We are able to catch an event like the kilonova 4 years ago, up to about 200 megaparsecs. And we are prepared for the next round of 4. And what I told you before, that with a significant increase in the chance of detection because of the capabilities of the LIGO tool. How is this connected with colibri? Well, DOTI is for detection only. We can cover a lot of sources each time. I mean, we know that each field can observe thousands of sources, and we can reject, of course, what are well-known stars, galaxies, quasars, blazars, etc. But if we have a candidate, an interesting candidate, we can have another follow-up. And if this is where colibri is important, because we can select some specific candidates just to do a follow-up with colibri and benefit from the observation. And I think I finish here. Thank you very much for your attention.
Thank you, Rosa. Stefan.
Yes, I have a small question. So if I understand properly, for the O4, you have no tile, so you go directly on the target. How long you will spend on which magnitude you can expect to have, which sensitivity you will have for O4?
Why are the
No,
O4?
For O3 you are tiling the observations. For O4 you have no tiles, so you go directly on the position. How long you spend with DOTI? You spend all the night, all the possible.
We observe when it's possible. I mean, if we have the chance to observe all the night, of course we do, but the probability is indicator.
But your question, Stefan, I think, is your question, is the observing time limited?
Yes.
No.
And also, which magnitude you can expect to have?
The limiting magnitude,
yes. An average you can expect to go to, because here you are saying that you are limited to 20.5.
We can achieve at least one more magnitude, at least.
So you can expect to be between 21.5 and 22. It's not linear.
I don't know if 22, but 21, yes.
Okay, thanks.
Okay, thank you, Stefan. Any other questions for Rosa? So can you go back to the slide where you had the rates, the expected rates there? Okay, so this is, okay, so you have the three types of sources. Right, so one, you had 6. Okay, so when you said 1 per day, it's like the high end of the number of detections where you said 3 to 6 alerts per week. Okay, so 1 per day is the absolute maximum, right? It's the high end of this range.
Yeah.
Okay, but that's for binary black hole mergers, right?
Yes.
For binary neutron stars, you have 10, and the range is 0 to 50. Okay. That's like 1 per week. Okay. All right. Thank you. Arnaud, you have a question?
No, it's not a question, but just a quick information. First, I would like to insist on the fact that I am not sure at all about the truth about what I will say. If I remember well, I heard from Bertrand Cordier, that the Japanese will not be fully ready and performing well for the next run of 4. So that the immediate consequence is that the error box will not be so reduced, I'm afraid. But as I said, I hope to have understood well and I remember correctly. So I would advise you to check this information by your own.
Okay. Alan?
Yeah, just to make a comment. So we probably can't deal with rates so high. Okay, I mean, we're a small team. So this makes it very important that we concentrate on the most important events, okay, which are binary neutron stars and neutron star black hole events. And the moment it would be really helpful if LIGO and Virgo would give better information earlier on as to what their mass fits are. At the moment, we get very little information, and it's a source of frustration to us and many other observing groups.
Yeah. Agreed.
Damien is confirming the comment of Arnaud.
Of Arnaud. Yes, in the chat, he says that Kagra will start with a very limited sensitivity. And he says very, very limited.
Yeah, it's still around 1 megaparsec, 1 to few megaparsec at the beginning, 1 to 10 megaparsec at the beginning.
Okay, so Andromeda. All right, Diego, got.
Yes, I wanted just to confirm this. I had a chat with the responsible of Virgo last week, and she confirmed me that indeed we have to expect the same number for 04 as for 03. Actually, exactly the same number in terms of rates and in terms of error boxes, because we finally, the addition of Kagra unfortunately doesn't bring a lot. And well, the distances will be a little bit farther for Virgo and LIGO, but it's not really significantly different. I also reanalyzed the O3 data, and the bottom line is that it will be 04 will be really like 03.
Okay.
Oh.
Right. Well, completely saturated with events then, but okay. All right.
I have a last. Can I have a last question on DOTI? Just to understand, which science are you doing except for the alert? On how you manage the data processing and so on, because it's huge. You have huge field of view. How is the organization of the team?
Well, NAT produce redox, which separate what are interesting or not targets related with another catalogs. Then for the rest of the sources, Maggie, who is here, Simone Di Chiara, and me specifically check by hand the light curves just to, yeah, a huge work. At the beginning was around 1,000 of candidates, but we have now distance only, and not improves the pipeline every month, and it works better now.
Which other science are you doing with DOTI? Which kind of subject? How it works, DOTI, for the how do you define your observing plan, except for the alerts?
Alan, you want to comment on that?
Yeah, we're doing two other kinds of science. We're doing other kinds of alert science. We look for Fermi GBM, GRBs, we look for Hawk GRBs, and we look for neutrino sources. We also have non-alert science, which is mainly young stellar object variability in very large fields, obviously. We have fields in W3, we have fields in Orion, we have fields in Monocerontes. Yeah, that's what we do.
Okay, thanks.
Okay. All right. Well, if there are no other questions, then that's the end of today's session. And we would start again tomorrow. What is it, Rosa? 9:20 or 9?
Yes.
9:20.
9.
9 in Mexico City, 7 in Canada, and 4 p.m. in France. Okay. So we'll see you tomorrow then, and thank you all very much.
Thank you. See you tomorrow.
Thanks.
Have a good day.
Thank you. Bye bye.
Bye.
Good night.
Bye.
Bye.
Adiós.
Hasta luego. Buen día.
Bye. Hasta luego. Buen día.
Bye.
Bye bye. Bonjour.